Minasan, konnichiwa, Zamurai Engineer desu. So let us continue this particular discussion about comparison of different materials. It's very important to give us the actual comparison, how strong, how dense, how lightweight, and other related comparison properties. Okay, so we have talk about metals, talk about polymers, talk about natural materials, talk about polymer foams. So polymer foams is weaker than most of the natural materials, but take a look, cork is the weakest in this example, in this group. Okay, so what about composites? Composites are those materials which are combination of two or more different materials. So that is what we mean by composites. So composites, this is the part of composite. This loop is the composite part. Okay, so composite part is what? Having a very good strength capacity, almost comparable with the steel, but lightweight. So the weight is very light compared to steel, so about 4 or 5 times. Okay, lightweight. Okay, so what about technical ceramics? Okay, ceramics. This loop is the technical ceramics. Okay, technical ceramics. So we have boron carbide, tungsten carbide. So this type of materials are the strongest material. This type of material, boron carbide, tungsten carbide, they are used as tool steel. They are used as what, cutting, as the cutter for tooling. Okay, they are cutter. Okay, so silicon carbide, tungsten carbide, boron carbide, okay, glass ceramic, even glass ceramic. Take note, glass ceramic is stronger than steel. Take a look. The red portion is steel. This is glass ceramic. Okay? Okay? Actually, we can use ceramic as a cutting tool, like silicon carbide, like tungsten carbide, like boron carbide. So, silica glass is actually better than steel. But do you know silica glass? Okay? Okay, the major component of sand. Okay, silica glass. Okay, so alumina. Okay, so these are the comparison. Now, let us proceed with more in-depth comparison guide. How we have to compare materials. Okay, for example, we have what? We have the horizontal axis as what? Epsilon. Epsilon is what we call strain. Epsilon is a Greek. It is a Greek letter. Epsilon represent strain. Okay. So this is a Greek letter sigma, which represent stress. So this is a what? Stress strain diagram. So stress strain diagram. So from 0 straight up to point what? Proportional limit. Okay? Proportional limit, then going to E, point E. Take note. Point 0, point P, which means proportional limit, to point E, which means elastic limit, point Y, which means yield stress. Okay? what is the next point? The next point is U, which means ultimate stress. And finally, point F, fracture or R. Point R or fracture. So usually point R is fracture, meaning it is now what? Damaged, broken. It's now broken here. The steel crystal structure will be what? Broken. Okay. Now, you can easily memorize this by pure. Okay. P, pure. So this is actually R. R, I think is what do you mean by R? Fracture stress. So it is fracture stress, but it is represented by R. Okay. Okay, so pure, it is called pure. So P, proportional point, then elastic limit, yield stress, then ultimate, then fracture stress. So pure. So up to the point of what? Almost between elastic and yield stress, right? Almost between that, there is a line which signifies this is elastic behavior. Okay, so just before the elastic limit. Okay, so we have elastic behavior in that region. So that is what we call elastic region, because the behavior of steel is elastic. What do you mean by elastic? Elastic means the tension and compression has almost the same characteristic, only different direction. And also, if you stretch and release, it will return back to normal. That is what we call elastic behavior. Okay. Now, if you proceed further above the elastic behavior, okay, if you proceed further, meaning if you add more load, okay, if you add more strength, more force, if you add more load or more force, what will happen to the steel? It will not break. It will not break, but will deform. So there is now a deformation. So from this point to this point, there is a deformation. That is what we call plastic behavior. So because if you stretch plastic and release it, it will not return because it is plastic. Okay, that is the plastic behavior. It will have deformities. Unlike in elastic, if you stretch and release, it will return to normal. In plastic behavior, it is not broken, okay, but there is noticeable deformity. Deformity, increasing deformity, increasing deformity up to the maximum, okay, to the maximum strength that it can carry. So after reaching that point, the deterioration in its characteristic is going now to proceed, no? Deterioration portion. It will deteriorate faster. Take a look. From this point to this point, it is longer than from this point to this point. It is shorter. No? So the deterioration portion is shorter than the deformation portion. Okay? And then immediately it will become deteriorate, and then at this point it will be broken. R meaning rupture. R meaning rupture. So fracture or rupture is the same thing. That's why I call it R. It means rupture. So pure, no? Pure meaning R rupture. Rupture meaning it's now physically detached. It is now detached. So after ultimate stress, that region is what we call necking. Remember, I show you I already showed you last meeting or last week a picture of necking. When steel is being stretched, there is a necking that happen. If there's no necking, the steel is brittle. If there's necking, it is good because the steel is not brittle. Okay, brittle meaning glass-like, glass-like behavior. Brittle. Okay. Okay. So from this point to this point, that is what we call strain hardening. Okay. The steel will resist further. It will resist. It will resist. It is harder to. It's becoming harder and harder to what stretch. The yielding portion from this point to this point, this is where the plastic will easily yield. The plastic will easily yield. It could easily be stretched. But from that point to this point, this is hard to yield. The steel is harder to yield. No? Okay. And meaning this is the natural and complete behavior of steel. It's a natural and complete behavior of steel. From zero load, then going up to the proportional limit, elastic limit. After elastic limit, we have the elastic behavior. Okay, and then before yield stress, we have elastic region, elastic behavior. After yield stress, we have what? Plastic behavior. Right? So there are how many regions? There are two major regions, elastic and plastic. And under plastic, there are three sub-regions, yielding, strain hardening, and necking. Please take note of this. This is very important. Okay? And if we establish a different method of graphing, we can call this part, this is true fracture. This is the code for true fracture. This is the code for conventional fracture. This is the conventional one. This is true fracture. Later on, I may be able to tell you how this is computed, how the true fracture is computed. So later on. So material behavior. So this is now at the realistic. This is not realistic. This is just to show you the regions. But you can see the elastic region is very small. This is the what? This is the elastic region. This is the yield point. This is the yield point. The elastic region is almost negligible. From this point to this point, these are plastic regions. Okay, so almost negligible. This is a realistic graph. This is just to explain. This is an explanation graph. This is the real graph. Okay. Okay. So take note. This is the what? End of elastic or yield point. Okay. There are materials that is mild steel. Okay. Mild steel, we have what? This one, okay. So this is mild steel. Okay. Like this. Okay. So give me 1 minute. Okay, let's continue. We have the mild steel stress strain diagram. So we have the same proportional proportional, then elastic, then yield, then going to the ultimate, then rupture. Okay, we have proportional, we have elastic, we have yield, we have ultimate, and rupture. Same line, no? So that is what? Stress. Okay. What do you mean by yield stress? Upper. So yield. This one is yield stress upper, yield stress lower. So 38, 36. So this one is yield stress lower, yield stress upper. So from this point to this point, this is yield stress. So we're able to graphically observe the yielding. This characteristic is yielding. The yielding, it gave way. It gave way. It yields. Okay? So this is what? Proportional limit. So proportional limit is up to this point. So this is the proportional limit. So P. So P. So elastic limit is this one. Yield is this one. Okay. So ultimate and rupture. So therefore we have what? Elastic region. So elastic region is up to this point. After yielding from this point, it yields. Yielding means it will not return back to normal. Okay? The normal length will not return back. If you release the load, release the force, release the tension, will not return. Just like a rubber. Okay? If you stretch a rubber and release, it will return back to normal. Okay? But if you stretch the rubber so much, it will come to a point that it will not return because it already yields, and after yielding, it will reach the ultimate, then even rupture. Okay? And then we have what? Yield strain. Okay? 0.3 is the yield strain. Okay? So this is 0.5, so 0.3 is less than that. So this is what? Proportional limit. Okay? Which is 0.0012. Proportional limit. Okay? And so on. So this is rupture or fracture. Rupture or fracture. This one. So take note, actually this is in terms of KSI. You can research. Okay, this is your assignment. Please research and get a graph which is in terms of SI unit, and you can what? You can even memorize the values of the graph because it will not change. This graph will not change. Therefore, you can actually memorize this graph. Okay. Okay. What about stress strain behavior? Okay. The same graphical relationship, but with the third factor, which is temperature. Okay. What about if we hit the steel? 20 degrees Celsius is the ambient temperature in the United States. In our country, our ambient temperature is about 30. Okay, it's about 30 or 28 to 31. 28 to 31. That is our ambient temperature. So this is the characteristic of steel at 20. So about the same. This is a characteristic. About the same behavior. Okay. However, take note, if you increase the temperature of the steel. Okay, 200 degrees Celsius. Okay, there is a noticeable decrease in property, meaning in the stress capacity, strain capacity. Okay, 200. 300, there is another noticeable loss in strain capacity. 400, another noticeable loss. 500, that is too much. Actually, after 500, 550, that is the actually limitation of steel. So that's why in case of fire, steel is very much what? Susceptible to failure. It could easily what? It could easily go to what? To the fracture. So remember, this is what? More than 350. Okay? This is more than 350 giga Pascal. This is Newton per mm squared. That is equivalent to giga Pascal. Okay? So this is more than 350 gigapascal. Okay? And what about this one? This is about 250 gigapascal. So what happened? There is more than or about 100 gigapascal difference. Imagine that, 100 gigapascal difference. So 250 divided by, what is 250? Divided by 350. Okay? That is too much. That is about 70%. No? This is about 70% lower or lowering, decrease in capacity, and that is too much. The component will fail. Okay, component will fail. So what about if the temperature goes up to 600 degrees Celsius? Okay, this is only 150 gigapascal. So from 350 to 150. Okay, how many? 150 over 350. That is too much. 250 gigapascal reduction in capacity. That is a failure. No? So this is the influence of temperature on mechanical properties of structural steel. Okay. So challenge problem. Let us take our challenge problem. As you can see at the background picture, we have the background picture which show us the reflective sheeting. This is the sheeting that we can put over the highway or near the highway, and that is called chevron sign. Okay, so reflective sheeting. So these sheets will reflect when it receives light rays. No? It will reflect the light rays. So this reflective sheeting for chevron signs shall perform effectively for a minimum of blank years from date of publication and retain at least blank % of its original brightness. How many years is our capacity of reflective sheeting? This will fade. This color will fade. The reflectivity will fade. The original brightness will fade. How long? How many years? And how many %? Letter A, 6 years, 60%. Letter B, 7 years, 70%. Letter C, 5 years, 50%. Letter D, 8 years, 80%. Okay, so that's all with this current video. Again, this is Dr. EYPEI, preaching engineering for nation building.